Good day, everyone. Today we're still going to look at Chapter 7, but we're just going to focus on interference and diffractions. Now, of course, I won't go through all questions with you all. I'm just going to select a few questions that can show you how to solve the question that is related to interference and diffractions. Now, let us look at questions 11, a question from double slit interference. Questions A. In Young's double slit experiment, the light source simultaneously emits a blue light of wavelength 400 nanometer and a yellow light of wavelength 600 nanometer. The slits are 0.08 mm apart and the interference pattern is observed on the screen at a distance of 60 cm from the slit. Calculate 1. The distance of the first blue and the first yellow fringes from the central fringe. 2. The shortest distance from the central fringe where the yellow and blue fringes overlap. Now for questions 1, actually it's quite easy to solve it because you are given all of the information needed. So you are given the wavelength for blue light that is equals to 400 nanometer, the wavelength for yellow light that is equals to 600 nanometer, and it tells you the distance between two slits, which is the small letter d, it is equals to 0.08 mm apart, and the distance between screen and the slit, which is capital letter D, that is equals to 60 cm. Now, of course, you are given everything in different unit. The first thing that you should do, change everything into SI unit, which is meter. So next, we are going to determine whether our interference is a constructive or a destructive interference. If you look at questions 1, now it tells you first blue and first yellow fringes are formed. So you can see color. You can see blue, you can see yellow. Whenever you can see color, then we say this is constructive interference. Okay, so for constructive interference, the numbers of order for first bright fringe would be m equals to 1, and for first yellow, the m is also equals to 1. So now that we have all of the information needed, basically you just have to apply the equations, y equals to m lambda d over d, and then you substitute everything into the equations and you will get the answer, 3 mm and 4.5 mm. Next, let us look at questions 2. How to solve questions 2? It is asking for the shortest distance from central fringe where yellow and blue fringes are overlapped with each other. So when you have two colors shines through the double slit, there are multiple fringes, they might be overlapped with each other. Okay, that might be overlapped with each other. So this question is asking for the shortest distance from the central fringe, meaning that it's asking for the one that's closest to the central fringe. So how are we going to solve it? We are not given the numbers of order, we are not given anything. We were just told that they are overlapping with each other. Then what are we going to do to get the relationship given in this solution? 2y yellow and 2y blue. So the first things we have to see which fringes are overlapping with each other. So to determine that, now let us go back to the main questions. We need to find out what is the information that we have right now. So now you are given two light, and now the key part is these two light, they are using the same experimental setup. Okay, they are shine on the same double slit, and then the screen is located at the same position. Meaning to say, the small letter d and the capital letter D for both color, they are the same. Okay, so we know that the equation is y equals to m lambda d over d, and when they are overlapping with each other, what we can say is y yellow equals to y blue. So now let us substitute the equations into here. So y yellow, I have m yellow, which is the unknown value. Lambda yellow given in the question, which is a 600 nanometer. And then capital letter D and small letter d without subscript because it is the same for both color. and then equals to M blue lambda blue D over D. Okay, so let's cancel out the things that we have first. So capital letter D and small letter d, you can cancel it out. And then after that, we are left with my lambda y, mb lambda b. So what are we going to do next? My lambda y equals to mb lambda b. So now let us try to find out what is the ratio of the order for these two different wavelengths. So rearrange the equations. We have lambda y over lambda b equals to mb over my. Lambda y is 600 and then lambda b is 400. So what we have right now, mb over my is a 600 over 400 nanometer. Okay, so you can simplify the value. Simplify it, you will then obtain 3 over 2. So what does it mean by 3 over 2? Well, it means that the third order for blue fringe is overlapping with the second order of the yellow fringe. Okay, so third order of blue fringe, okay, your third blue is overlapped with the second order of the yellow fringe. That is what we have based on our ratio. So now that you have it, then you can calculate it. Okay, you can calculate it. But how? Now from questions 1, we know that the location for first blue is 3 mm. Therefore, the location for third blue would be 3y1 blue. Okay, equals to, now the location for first yellow, we got 4.5 mm. So the location for the second yellow would be 2y1 yellow. Okay, so now you see we have already got these equations, the equations that is same as the one given in the solution. So substitute the values into the equations and then you will get y, where they are overlapping, is equals to 9 mm. So that is the final answer. Next, let's look at questions 18. It is also a question from double slit interference. Now, questions A. Two narrow slits separated by 2.4 mm are illuminated by a light with lambda 512 nanometer. The screen is placed 6.5 meter from the slit. Determine 1. Distance between adjacent bright fringes on a screen. 2. Distance of the fifth dark fringe from the central bright fringe. So obviously now for these questions, you have central bright fringe. So now let's see how are we going to solve this question. If you look at questions 1, the key point, the key words to solve this question is adjacence. Okay, so we are not given the wavelength, the numbers of order, sorry. We are not given the numbers of order, but what we do know is that now you have two fringes. They are consecutive fringes, consecutive bright fringes. They are adjacent, they are continuous in terms of the numbers of order. So when you have two adjacent bright fringes, then straight away you can apply the equations delta y equals to lambda d over d. So remember, this equation is only valid if you have two consecutive same color fringes. Okay, so for example, if question is asking for the distance between two adjacent dark fringes, two adjacent bright fringes, two consecutive bright fringes, two consecutive dark fringes, then yes, you can apply this equation. So other than that, you cannot use this equation. Okay, so if the question is asking for adjacent bright fringe and dark fringe, then no, you cannot calculate it by using this equation. If question is asking for first dark and third dark, then once again, you cannot use this equation because they are not consecutive. Okay, the numbers of order, they are not continuous. So questions 1, apply this equation straight away, you can get the values already. Now let's look at questions number 2. Questions number 2, now you have fifth dark fringe. Okay, Now, the reasons why I choose this question is I want you to see what is the difference between bright fringe and dark fringe. So the distance of the fifth dark fringe from the central bright fringe. Now, in previous question, for first bright, we have first order. But when it comes to dark fringe, first dark is not first order dark fringe. Okay, so if you look at the diagrams on the right hand side, what we have, when you have first dark fringe, you have zero order. Second dark, it is a first order dark fringe. Third dark, it is the second order dark fringe. So when you have a fifth dark, what does it mean? So fifth dark fringe, okay, fifth dark fringe is not fifth order dark. Okay, that is what you have to know. So when it comes to fifth dark, it is equals to fourth order. Okay, fourth order. So in this case, what we have, m is equals to 4. Okay, m is equals to 4. So once you know what is the numbers of order, you then have to think, dark fringe, well, obviously it is destructive interference. So for destructive interference, we apply equations y equals to m plus half lambda d over d. Substitute everything into these equations, you will then get the final answer. Okay, 6.24 times 10 to the power of negative 3 meter. So that is the final answer for questions 18. So we are done with interference through double slit. Now let's look at interference of thin film. So question 17b. A soft film with refractive index 1.3 and minimum thickness 0.177 micrometer appears reddish under white light. Calculate the wavelength of light that is missing from the reflection. So how are we going to solve this question? The key part is the question is asking for the wavelength of light that is missing from reflection. It means what the question wants is actually destructive interference. Okay, so this is a question about destructive interference. But when it comes to thin film, other than determining the type of interference, we also need to find out what type of sources we have. So for this question, now let's look at the diagram on the right hand side. So we have soft film. Soft film is the second layer. So second layer, the n is 1.3. So outside soft film, of course, is the air, which is 1.0. Inside soft film is also air 1.0. So what happens right here now, you have incident light ray. When it hits point A, the light is going to travel from less dense mediums towards denser medium. How do I know? Based on the numbers of refractive index. So first layer you have 1. Okay, so 1 towards 1.3 from less dense towards denser medium. So the reflected ray at point A, it will undergo pi radian phase change. Okay, because it's traveling from less dense towards denser medium. Part of the ray being reflected and part of it will be transmitted and keep moving forward. So the one that is being transmitted, it will move towards second layer. And when it hits point B, what happens is that now the light is going to travel from a denser medium towards a less dense medium. And at point B is because from denser to less dense medium, the reflected ray, it has no phase change. Okay, so from denser towards less than, the reflected ray, it has no phase change. From less than towards denser medium, the reflected rays, it undergoes pi radian phase change. So when you have one undergoes phase change and one no phase change, we say we have anti-phase sources. So for anti-phase sources, if you want to get destructive interference, then the equations that we should use is 2nt equals to m lambda. Alright, so for n, we are going to use the n from the second layer, which is 1.3. But how about m? Now, if you look at this equation, okay, and the information is given, the key point is now you have minimum thickness that is equals to 0.177 micrometer. Minimum thickness, now let's look at the relationship between thickness and order. So based on the equation, T is directly proportional to M. So if you have T mean, then M should be minimum as well. So for this equation, the minimum n, it should be 1. Okay, it cannot be 0 because if it is 0, then the thickness would be 0. So the minimum values of M that can be used in this equation, it's equals to 1. So by using M equals to 1 and the information given in the questions, you can then determine the values of wavelength, which is equals to 460.2 times 10 to the power of negative 9 meter. So that is the answer for question 17. Next, questions 19 is also a question on thin film. So questions B. A flat glass with index of refractions 1.5 is coated with a transparent material of refractions index 1.25 in order to eliminate reflections of light of wavelength 680 nanometer. Determines the minimum thickness of coating. So how to solve this question? Once again, it wants to eliminate reflection. Means that it doesn't want to see color. Okay, so it doesn't want to see the color with 680 nanometer. So that this is a destructive interference questions. And once again, the question mentions minimum thickness. So minimum thickness means that we want minimum order. But minimum order, it depends on the type of the equations that we're going to use. So now let's see which equation should we use. So we have done determining the type of interference. So what we have right here is destructive interference again. And then let's look at the diagrams on the right hand side. So questions mentions, now you have a flat glass, okay, flat glass, and you coat it with a transparent material. So this transparent material is located on top of the glass. And on top of the transparent material, obviously, is the surrounding. Okay, so you look at the surrounding. Now the surrounding is air. So meaning to say, N1 is equals to 1. N2 is the materials, the transparent material, which is 1.25. And then N3 is 1.5. So what happens right here? Now I have incident light ray when it hits point A. Okay, so it's from less than towards denser medium. So the reflected ray, it undergoes pi radian phase change. And as the light keeps moving and hits point B at the second layer, the light is now traveling still from less than towards denser medium. So once again, the reflected ray, okay, it also undergoes pi radian phase change. So when you have two light rays, both undergoes pi radian phase change, then we say it is in phase source. So if you have in phase sources and it undergoes destructive interference, then the equations that you should use is m plus half lambda. So questions mentions minimum thickness. Well, we know thickness is proportional to order. So minimum thickness, you want to use minimum order. When it comes to m plus half lambda, the smallest values of m that you can use now and still give you a non-zero thickness is m equals to 0. So when you have equations m plus half lambda, the minimum m should be 0. If the equation is m lambda, then the minimum m should be 1. Okay, so the reasons why we can use 0, I repeat again, that is because if you use m equals to 0, you can still get a non-zero thickness in this case. So substitute everything into the equations. Okay, you will then get the minimum thickness that is equals to 1.36 times 10 to the power of negative 7 meter. So that marks the end of interference. Now let us proceed to diffractions. So questions 10 is a question on single slit diffraction. Questions 8. Light 450 nanometer wavelength is incident on a slit 0.24 mm wide. A screen is placed 2 meters from the slit. Questions 1. Determines the positions of the first dark fringe. Questions 3. Calculate the width of the central bright fringe. So how are we going to solve these questions? If you go through the questions again, you will see that now you are given lambda that is equals to 450 nanometer, and then the slit of the width A is equals to 0.24 mm, and capital letter D is equals to 2 meter. That is the distance between screen and the single slit. So questions 1. Determine the positions of the first dark fringe. Now when it comes to single slit diffractions, you have to be careful with the numbers of order. In double slit interference, first dark fringe represents zero order dark. But when it comes to single slit diffraction, first dark fringe, it represents first order dark. So meaning that now what we have is m equals to 1. Okay, m equals to 1. So by using all this information, you then apply the equations y equals to n lambda d over a. Straight away you can get the answer for questions 1, which is equals to 4.5 times 10 to the power of negative 3 meter. So if you look at questions 3, now calculate the width of the central bright fringe. How to calculate the width? So I want you to take note. Even though it says central bright fringe here, but when it comes to single slit diffractions, zero order, it does not exist. Okay, we don't have zero order in single slit diffraction. Then how are we going to calculate the width of a central bright? So let's look at the diagram on the right hand side. So this is a diagram of a single slit diffractions. Okay, and then this part, it represents the central fringe. So when we want to calculate the width, the size of the central fringe, what are we going to do? We try to find out where is our first dark. Okay, so this is the positions of the first dark. So first dark only happens at one point. Okay, if you look at this diagram, so the graph, you only have one minimum point, and that is where we have the dark fringe. Okay, a total cancellation is happening at that one point only. So if you are managed to determine the positions of the first dark fringe, okay, so then you should be able to calculate the width. How? So this is your first dark, y1, y1. Remember, y1 you calculate it from the center. So from here to here is 1 y1. From here to here is 1 y1. So the width of the central fringe, w, is equals to 2 y1. 2 times of the first dark fringe, sorry. Okay, 2 times the positions of the first dark fringe. So therefore the answer is 9 mm. Questions 18. It is also a question on single slit diffractions. Now let's look at B. A monochromatic light of wavelength 620 nanometer is incident on a single slit and forms a diffraction pattern on a screen 1.2 meter away. The distance of 7 dark fringe from the central maximum is 18 mm. Determine 1. The size of the single slit. 2. Distance of the second bright fringe from the central maximum. So if you look at these questions, now you are given a wavelength, and then you notice that the screen is located 1.2 meter away from the slit. So capital letter B is 1.2 meter. And then the next statement, the distance of 7 dark fringe from the central maximum is 18 mm. So what does it mean? That is your Y. Okay. But then the things that I want you to be careful, okay, now if you remember the things that we have seen just now, 7 dark fringe. When it comes to single slit diffraction, the numbers of fringes is same as the numbers of order. Okay, so let's look at the diagram on the right hand side. So if you look at this diagram, first dark, it represents first order dark. Second dark, it represents second order dark. Okay. It means that now when it comes to 7 dark fringe, what you have is m equals to 7, and therefore the y given right here is y7. So the size of a single slit, so the question is asking for small letter a. So you have y, you have d, you have lambda, you have m, therefore you can use it to find a by applying equation for dark fringe, which is n y equals to n lambda d over a. So this is the equation for dark fringe. So questions 2. The distance of second bright fringe. Okay, so now you are looking at second bright fringe. So what is the numbers of order? Once again, let's look at the diagram on the right hand side. So when it comes to single slit diffractions, the numbers of fringes basically is same as the numbers of order. So first bright is equals to n is equals to first order, n equals to what? Second bright, n equals to 2. Therefore, when it comes to this question, second bright, m it's also equals to 2. But for bright fringe, we apply equations y equals to n plus half lambda d over a. So by using these equations, you can then obtain y equals to 6.44 times 10 to the power of negative 3 meter. So that is the answer for questions 18. So now let us proceed to the last part in chapter 7, diffractions grating. So questions 14. A. A beam consists of two monochromatic light, 400 nanometer and 600 nanometer, is incident normally on a diffractions grating which has 540 lines per mm. So calculate 1. Angular separation between the first order diffractions of the light. 2. Highest order of diffractions that can be observed with 600 nanometer light. So how are we going to solve it? Now, first of all, you have to understand what does it mean by angular separation. So angular separation, it means the question is asking for the angle. So it is asking for the angle between the first order diffractions of both light, the light of 400 nanometer and 600 nanometer. So if you look at the diagrams on the right hand side, so angular separation, okay, it represents the angles right here. So you are going to calculate the angle from central bright until first bright. And then after that, what are you going to do? You repeat it again for 600 nanometer and then you subtract the value. And it will give you the final answer for questions 1. So basically, this is how you do it. You calculate the angle for 400 nanometer, that is the angular separation for 400 nanometer, and then you repeat it again for 600 nanometer. Now that you get the first order, okay, the angular separation for first order for both type of wavelength, then you just subtract it and get the difference between the two angular separation. So questions 2. Now questions 2, the key point is the highest order. So highest order means that the question is asking for the maximum order. Okay, so how are we going to determine the maximum order if you are going to use the light of 600 nanometer? So when it comes to the questions like this, let us go back to the equations. So now you are given equations d sine theta equals to n lambda. When it comes to asking for maximum or minimum value, usually we can play with sine theta right here. Since the question is asking for the maximum value, then what is the angles that can give us the maximum value? Well, if you have sine theta, then maximum theta that we can use is sine 90 degree. Because sine 90 degree gives us 1, which is the maximum value that we can have. So by assuming angles equals to 90 degree, then you can get maximum order, okay, and max. But if you look at the answer, when you substitute theta equals to 90 degree in the equations, it gives you 3.09. When it comes to numbers of order, we don't want to have decimal places. Okay, we don't want decimal points right here. So you have to round off the value. Therefore, the highest order right here is equals to 3. Now, when it comes to round off the value, okay, be careful as well. I want you to keep it in your mind. As long as it hasn't reached the next value, then you round off as 3. So for example, if you calculate the values and you got 3.95, for example, as long as it hasn't reached the values 4, then you round off as 3. Okay, so that is the rules of determining the values of order. Last questions. So question 16 is also a question on diffractions grating. So questions 8. Orange light of wavelength 600 nanometer is incidental to a diffractions grating having 3500 line per cm. Questions 1. Calculate the slit separation. Questions 2. Determines the maximum number of bright fringes that can be observed. Questions 3. How can the number of bright fringes can be increased? So questions 1. the slit separation. So to calculate slit separations D, if you look at the questions, now you are given n numbers of line per cm. So you can just calculate it by using 1 over n. But be careful with the unit. If you calculate D by using line per cm, then D should be in cm. If you calculate it by using lines per meter, then D will be in meter. Okay, so in these questions, you calculate D by using lines per cm. Therefore, as you can see here, okay, as you can see in the solution, 1 over 3,500, it gives you D in terms of cm. Okay, so 2.86 times 10 to the power of -4. You then convert it into meter. Now in exam, it is up to you whether you want to convert it into meter or not, as long as the questions didn't ask you to state in a SI unit. Okay, so you can leave it in cm, that is fine. So questions 2 determines the numbers of bright fringe that can be seen. Okay, so maximum numbers of bright fringe that can be seen is not the same as the maximum order that can be observed. Maximum numbers of bright fringe that can be seen, if you look at the diagrams on the right hand side, now numbers of order, it only gives you the numbers of fringes on one side. If you want to calculate the maximum numbers of bright fringe that can be seen, you need to take into considerations both sides and also the central fringe. Therefore, to calculate maximum numbers of bright fringe that can be seen, first, you determine the maximum numbers of order that can be seen first, because it will give you the numbers of fringes that can be seen on one side. So if you calculate it, you will get n equals to 4.676. You round off as 4, since you want to calculate the numbers of bright fringe that can be seen. So 4 plus 4 plus 1 equals to 9 fringes. Okay, so the 4 on one side, 4 on the other side, plus 1 central fringe. So total numbers of fringes that can be seen is 9 fringes. And then question 3, how can the numbers of bright fringes that can be increased? Okay, so since the numbers of bright fringes, it depends on the numbers of order, therefore you just have to look at the equations. D sine theta equals to n lambda, and then you check the relationship between n and D, and also n and the lambda. Okay, so since n is directly proportional to D, you can increase the numbers of bright fringes by increasing the slit separation, and then n is inversely proportional to wavelength, so you can decrease the wavelength to increase the numbers of fringes that can be seen. So that is the answer for question 16. That's all for this slot. Thank you for watching and good luck in your PSPM.